Assalamualaikum and hi everyone. Today, I'll be presenting our project on microwave filter design, specifically focusing on low pass and band pass filter. Before we start, let me introduce to you guys my group members. FAREEQ NAIM, Aieenna and FAIZUL AKMAL. Moving into introduction, this project covers the complete design cycle of a microwave filters, from theoretical calculation to practical microstrip realization and ADS simulation. We designed a fifth order Chebyshev low-pass filter using insertion loss method. The filter is engineered to pass signal below 1.5 GHz while providing sharp stop band attenuation of at least 50 dB at 4.3 GHz. Now, why do we need distribution design? At high frequency, standard lump components like inductor and capacitor fail due to parasitic effects. So we transform our design into a practical microstrip layout using two key techniques, Richards transformation and Kuroda identities. We then optimize the final layout parameters using the ADS tuning environment to match real-world substrate conditions. Ultimately, this project demonstrates how precise RF filter design directly improves signal quality, reduce network interference, and minimize power loss to support modern energy-efficient communication technologies. The project requirement for our low-pass filter were clearly specified. We need to create distributed transmission line design using Richards transformation and Kuroda identities alongside lump design. The specifications are cut-off frequency 1.5 GHz, stop band attenuation 50 dB at 4.3 GHz, passband ripple 0.5 dB equal ripple. And importantly, we were required to use all open stub in the design. Now, let's look at the calculation. For a Chebyshev response with 0.5 dB ripple, we first needed to determine the filter order. Using the Chebyshev attenuation equation, we calculated the required filter order n. Based on our specification, we found that n equal to 5 was sufficient. From the 0.5 dB ripple prototype table, we obtain the G value. G1 is 1.7058, G2 is 1.2296, G3 equal to 2.5408, G4 is 1.2296, and G5 is 1.7058. We then scale this value to our actual cut-off frequency of 1.5 GHz and characteristic impedance of 50 ohms. Here we see the topology of our lump low-pass filter. This is fifth order Chebyshev filter using a ladder network configuration. The circuit alternates between series inductor and shunt capacitors, following the G values we calculated earlier. This slide shows our lump low-pass circuit simulation in ADS. You can see the schematic with the actual component values calculated from our prototype parameters. The series inductors and shunt capacitors are arranged in the ladder topology. This is the simulation result for our lump low-pass filter. Let me highlight the two key measurement markers. At M2, positioned at our cut-off frequency of 1.5 GHz, we see S21 equal negative 0.49 dB. This is excellent. It means the filter pass signals in the pass band with minimal loss, staying well within our 0.5 dB ripple specification. Now, look at M1, positioned at 4.3 GHz. This is our required stop band frequency. We archive S21 equal negative 59.287 dB. This is significant because it exceeds our specification of 50 dB attenuation at 4.3 GHz by almost 10 dB. The filter provides very strong rejection of unwanted high frequency signal. This confirms that our fifth order Chebyshev lump design successfully meets and even surpass both the passband ripple and stop band rejection targets. The sharp roll-off between 1.5 GHz and 4.3 GHz demonstrate the advantage of the Chebyshev response over a Butterworth filter of the same order.
Assalamualaikum. My name is FAREEQ dari ZULKIFLI. Number metric B122410437. Okay. The slide is Kuroda entity simulation. Now we move to the Chebyshev design. This shows the circuit after applying Kuroda entity. Here what we did using Richards transformation, we convert series inductor to series short stop and shunt capacitor to shunt open stop. Then we apply Kuroda second entity to convert each series short and stop into a more practical shunt open to stop configuration. Okay, the transformation interaction unique element and result in a cascade of transmission line and shown open stop, which is exactly what we need for practical Microsoft application. Okay, next, corona entity graph simulation. This shows the simulation result after the corona transformation. We can see the frequency response maintain the necessary characteristic. The passband ripple and stop band attenuation preserve, confirming the out transformation was successful. However, you may notice some difference compared to the ideal lumped response due to the disparate nature of the design. Okay, next is layout corona entity. Here is the physical layout of our discrete filter. This is the microstrip realizing using transmission line and open stop. The layout shows the actual geometric dimension calculated based on our substrate parameter, the electric constant of 4.4, substrate hinge of 1.6 mm, and conductor thickness of 5 micrometer. The layout demonstrates how the theoretical circuit translates to a practical fabricable design. Okay, next is calculation corona. These are the detailed calculation for the corona transformation. The formula used is n squared equal 1 plus z1 per z2. For a step transformation, we calculate the new impedance value. You can see the calculation for each section, showing how the series stop were converted to shunt stop with appropriate impedance transformation. Okay, next, this slide shows the complete step-by-step calculation for our discrete design. Okay, next is following Richard transformation. We apply corona entity in sequence to option the final transmission line, impedance, and lines. Next, I pass to my friend.
Now we move to the band pass filter. Unlike the low pass filter, the band pass filter will not be implemented in distributed form. It's enough that it's designed with lump element only. The specifications are center frequency 1.5 GHz, bandwidth 160 MHz, response maximally flat Butterworth order and equal to 5. Next, I will explain the calculation for design a 5-order shift-by-shift band pass filter based on the formula in image. Our design parameter are 50 ohm reference impedance, 1.5 GHz center frequency, and fractional bandwidth of 0.1067. First, let's look at the shunt element in G1, G3, and G5. Each prototype value yields a parallel inductor capacitor pair. For the symmetrical outer stage, G1 and G5 is 0.618, we get a shunt inductance of 0.619 nanoH and a capacitance of 12.29 picofarad. For the center stage, G3 2.0, the value changed to 0.283 nanoH and 39.78 picofarad. So the next is the series element for G2 and G4, which connect the shunt stage using series connected components. Due to symmetry, both stages use a prototype value of 1.618. This results in an identical series inductance of 80.45 nanoH and a very small series capacitance of 0.14 picofarad. In conclusion, by alternating these 3 shunt and 2 series LC network, we successfully realized our 1.5 GHz band pass filter. Here the ADS circuit schematic for our lump band pass filter. You can see the ladder network with series LC section and shunt LC section. This is a 5-order Butterworth band pass filter with the component value we calculate. Next, this slide shows the simulation result for the band pass filter. We can see the band pass centered at 1.5 GHz with bandwidth of approximately 160 MHz. The filter shows the characteristic maximally flat response in the bus band with minimal ripple. The rejection outside the bandpass is good, demonstrating effective bandpass filtering. The insertion loss in the bandpass is low, confirming that the filter meets the design specification. So next, the simulation showed the insertion loss response, or S21, plotted against frequency using ADS. This graph verified the performance of our 5th-order bandpass filter design. We have placed 2 markers, M1 and M2, to identify the cutoff frequency at the band edge. Marker 1 is at 1.4 GHz with an insertion loss of negative 3.589 dB, and marker 2 is at 1.580 GHz with an insertion loss of negative 2.530 dB. This point tightly bound our intended 1.5 GHz center frequency in actually bandwidth of 160 MHz. This closely aligns with our fraction bandwidth calculation. Furthermore, the step roll off outside the bandpass demonstrated excellent selectivity, confirming that our calculated component value effectively isolate the desired frequency range. So the conclusion is we successfully designed and verified a fifth order share by shift low pass filter meeting the 1.5 GHz cut-off requirement. We effectively utilize Richard transformation and Kuroda identity to transform theoretical lump element into a highly practical realizable microstrip and transmission line structure. We demonstrated proficiently in using advanced design system ADS for modeling, S parameter evaluation and layout optimization via turning tools. The project has given us valuable hands-on experience in microwave filter design from theoretical calculation through the practical implementation and simulation.